Today we are going to work on the problem-solving strategy with a common force problem. So you'll see how to use the 6 steps that we presented in the previous video. For today's question, we have a custodian pushing a trash can that is 7.8 kilograms across the floor. It's going to apply an 86 Newton force at an angle of 35 degrees below the horizontal, and the coefficient of friction between the bottom of the trash can and the floor is 0.41. And the goal here is to eventually get the acceleration of the trash can, but we don't want to start at the end. So we're going to start with our problem-solving process. The first step was to have a big diagram or big picture of the problem. So since we don't already have a picture here, it might be just useful to sketch a general picture of just a person maybe pushing what looks like a trash can. Okay, you got your floor. So maybe they're pushing down at an angle. So just a little picture so you know ideally what is happening in the story. So now we'll do the step 2 of the process, which is starting the free body diagram for our object in question. So our object, since we're solving for the acceleration of the trash can, we're going to do a free body diagram for that. So I'll start off with my dot for the trash can, or you can use a little box if you'd like to do that too. Always get the weight of your object in question. So we've got our mg, gravity, always pushing straight downward towards the center of the earth. And then you can get all of your other contact forces. So anything else that's interacting with our object. I know that it's being pushed across a floor, so I've got a floor there that's pushing it up. We usually call that the normal force. Okay, we'll just call it a capital N. I know that someone's pushing the trash can down at an angle, and it says that that angle is 35 degrees below the horizontal. So if I imagine my horizontal line being here, kind of make a little line for a horizontal, it's going to be 35 degrees below that. So if I go, put a little arrow here, I can go ahead and label this with a 35 degree angle, and we can call this our applied force. I'll just call it FA. That's your push force. Okay. It does indicate in the problem that there's also a roughness to the surface, so this has a coefficient of friction to it. So that tells us that this is not going to slide super quickly, but there's going to be a little bit of resistance. So your frictional force will act against that. I'll call that Fk for kinetic friction since it's moving. And then we want to just double check that there's no other things in contact with our object pushing or pulling on it to get into our diagram. So that's our free body diagram. So once we have our free body diagram completely done, we are ready to go and to move on into step 3, which is choosing a coordinate system for our solving process. This is where you want to go back and double check in the question, what is it that you're actually solving for? So we're looking for the acceleration of the trash can. And we know that acceleration is a vector. So there's going to be a direction tied to whatever its rate of change is. So we need to decide here how we can kind of simplify this to where our acceleration vector is all in one direction. So if we think about how this trash can is moving, even though we have a downward force pushing it into the ground, we've got the floor pushing it up, we know weight's going downward. If we think about this, if our person's over here pushing downward at this angle, which way do we think the trash can is going to go? And hopefully you've decided in your brain at this time that it's going to move overall in that rightward direction. So ideally it would be smart to make that our positive x direction. We're assigning our acceleration to the right, making everything else work like a normal math coordinate system to oppose that. So if your positive acceleration is to the right, then you'd have just like a graph, negative x, a line perpendicular to your x-axis, your positive y will be up, your negative y will be down. So it's just like you would graph something on a line for math. So that's our step 3. Now that we've decided what our coordinate system is for step 3, we can move on to step 4, which is setting up Newton's second law of motion. And just a little quick reminder on what that is. The sum of all of our vector forces are related to mass and acceleration in the form of what you'll see as Newton's second law in this equation. But there's a lot that goes into this. We have to establish all of the forces in our directions that we've already assigned. Because ultimately we know, and we've predicted, that our acceleration is tied to this positive x direction. So I'm really concerned with how those forces relate to each other with the x direction. So setting up two different equations here. Start in the x direction. I want to look at adding up all of these vectors, all of these arrows that are pointing in different directions. I see that I've got an applied force that's going in this downward direction, but it's not perfectly to the right. So this is where those vector components come in handy here. We can use a component vector for this applied force, which would be kind of this x component here. I'll just call it fx for now in the diagram. Okay. And then there would be a y component too. So we can see that not only is the person's applied force applying something to the right, but it's also pushing down inward into the floor as well. So we've got a downward y component here too. So that ends up kind of creating that a vector triangle with your components, which you guys are pretty good with at this point. So looking at the x direction, I know that fx is going to be the side adjacent component to our 35-degree angle. So I'm going to say the applied force times the cosine of 35, or you can put theta in there if it's an unknown angle. So that's in one of our forces is in the x direction. Then I look for some more, anything else along that horizontal axis. And we've got our friction force. It's going in the opposite direction. So since that's in the opposite direction, I can't add these together because they're not working together to move the trash can to the right, but the friction's resisting in the opposite direction. So I'm going to subtract that frictional force, minus Fk. All right. Then if we look at anything else, so is there anything else in the x direction? I don't see anything. There's no other forces in that portion of the coordinate system. So I know that the sum of all of these forces are going to combine to be that mass times acceleration ratio. So we've got m times a. All right, so now that we have our x direction done, again, our acceleration we've already established is associated in that x direction. So now we can do everything in the vertical portion. So we've got set up another little list of equations here. The sum of all forces in the y direction. So anything up and down. So I can see my normal force is going up. Typically we say up is positive and down is negative. So I know I have a normal force there. It's a positive direction. Then I look at anything in the downward direction or upward direction working with or against it. Nothing else going up. I see I've got weight going down, so I'm going to subtract the weight for the same reason we subtracted friction in the x direction. And then I also have to remember that this push force is not just pushing perfectly to the right, but that it is applying a force downward too. So we have two forces here that are acting in the downward direction against this normal force. So I'm going to subtract that y component as well. So it's our applied force, but it's the y component of that. So it's opposite to that 35-degree angle. So I'll say sine 35. And then I'll look for anything else in the up and down direction, double check. I don't see anything, so I think we're good. And then together, that would be mass times acceleration in the y direction. However, this is where choosing that coordinate system can really come in handy, because one of these, most often, is probably going to end up being 0. If we think about the direction where this trash can is moving, we've already established that the trash can is just going to move to the right. So that tells me that all of our acceleration is really tied to this x direction acceleration here. The trash can itself doesn't lift off the ground at all. It doesn't get pushed down into the ground through the ground. So essentially this thing doesn't accelerate at all in the vertical direction. So we can go ahead and say that this equation not necessarily is just equal to m times ay, but it's actually equal to 0. Because in this problem, ay is equal to 0. So now we've successfully set up Newton's second law of motion. That's step 4 of our problem-solving process. Step 5 is something that may or may not be necessary. It just kind of depends on the type of question you have. Step 5 basically says to apply those little intermediate equations to things if you think you're going to need them. So if we look at the things that we know and don't know, the things that are given to us here, the things that are unknown. If I think about my numbers here, I know the mass of the trash can. So these m's are eventually going to be something that I know. So we essentially know the weight of the trash can. The applied force of 86 newtons, this is something that's going to be a known variable that's given to us. However, we're not really told what the frictional force is. It doesn't say anywhere in the problem that the frictional force is some particular number. So it might be useful to remember that relationship for friction, which was that your kinetic friction is related to the coefficient of friction times the normal force. And it's the same for static. If this was not moving, you just use the static coefficient of friction. So this is where applying this little intermediate step might be helpful in solving this problem, because I can see here, this mu, that's something that we know, that's a given number, so it could be useful to me. So step 5, I'm going to go ahead and plug this intermediate equation into my work, because it's something extra that I can do. So if I rewrite, I should say, this x direction equation, so we've got 86 cosine of 35, and that's FA cosine of 35, minus our intermediate equation, which is that coefficient times the normal force. So I'll go ahead and write out our number there, 0.41 times n. We'll leave that as an unknown for now. And then that's it, equals mass times acceleration. Our mass was, what was it, 7.8. 7.8 times a. Okay. So now I have one equation here that is a little more detailed. It's got more stuff in it that's useful, more numbers. All right, so now we can do the same thing for the other equation in the y direction. Why do we need that second equation? Well, if we look here in what we've already set up, acceleration, something that we're solving for, that's the goal of the problem. But then I also have this unknown normal force in here as well. So anytime you have an unknown, you need another algebraic equation to help you get your numerical answer if you're trying to achieve one. So our second equation can come from our handy y direction equation, so I'm going to rewrite this and plug in as many things as I know about it. N is our unknown, minus mg, which is going to be 7.8 times gravity, 9.8, minus this stuff. And we had decided that this was going to be equal to 0. So this is where you can use a little bit of algebraic substitution, and you can solve for your normal force now. So by moving these numbers to the other side, combining them, you can derive a normal force, and it turns out that that normal force is equal to about 125.8 newtons if you calculator this out in your spare time. And then you can plug that 125 newtons into there, and then you arrive at your final answer. So I'll give you guys time. I want you to be able to work this question out on your own as well. So once you have finished rearranging some things, plugging in numbers on your own, you should arrive at a final answer of an acceleration around 2.42 meters per second squared. And then since it's a vector, I'm going to define this in our direction that goes with our story, which is to the right. And that's our problem solving strategy. Step 1, your big diagram. Step 2, free body diagram, Newton's second law in variable form, going with your coordinate system, and then usually the rest of it just kind of falls out for you.